getting fired up.
I don't know. Not really.
No, what I was asking is you just now starting to get streaming?
Oh yeah, I just started. Why, did you have a question first or anything, or?
Midterm, like problem 6 maybe?
Oh, okay.
I have a question about it. I was looking at it. I can't figure out how to determine one of the angles.
Oh, okay.
And I looked at some examples, and they were just given that angle.
That's right. And so the key there is if you look at it here, oops. Oh, here. Let's see. I think the book. I don't know if the book has X and Y, and Z. It doesn't really matter. When it comes up, it'll.
Because I looked at one of the examples, and at first I was like, well, it adds up to 90. Well, I added the angle that was given and the one that I'm given, and they came up to like 105. So it didn't follow that rule of like being a 90-degree angle. So.
Oh, is it up there? So, if you look at this, it's kind of a weird thing. Instead of going and finding it in the book, I could probably just list it out there. So the angles, so what you got is, oh, wait a minute. Oh. There's a relationship in there somewhere. If you look in there, it'll be boxed. Okay, that's supposed to be an alpha. Hang on. It has a relationship that says something like, and the reason that is simply because the reason that relationship exists is because if you, okay, I'm trying to think of his terminology, but cosine alpha is 1, shoot, what does he do? How does the term, is it nx? Oh shoot, I can't remember. Anyway, you'll find, let's say you have a vector out here, and it could be a length, 10. So what you end up doing is finding the unit vector. And so your unit vector might be, and I think he uses a small case u, is this. So let's say you found this unit vector right there. Well, so it turns out the unit vector is supposed to be 1. So if you look at it, you square this component, then square that component, then square that component, and they all add up to be 1. So if you're given that angle and say that angle and you don't know that one, you know that the thing has to line up to be 1. So you take this stuff, move it to the other side, and you get 1 minus, I don't remember. Anyway, let's just say gamma isn't known. So it'd be cosine squared alpha minus, and I wrote a plus. And then square root. But, yeah, that's supposed to be a beta. But that's equal to, yeah, that's equal to cosine. Yeah.
And then you have to inverse cosine.
Yeah, arc cosine of the square root and that's got to be equal to gamma. That'll give you that many degrees. And if you think about it logically, it makes sense. You're limited. Let's say, here you go. Let's take a really bizarre case. Let's say that's 45 and that's 45. If those two are 45, there's no other choice but to this to be 90.
Yeah.
So, but if this is 46 and that's 46, then you actually have two choices. It could pop out of the plane a little bit, out of the XY plane in other words, or it could pop down a little bit. And so it's going to be one of those two, you know, a little bit like 89 and 91. So there you got to figure out, okay, which one?
Which one is it?
Right. And so this, it's limited by that. And that's pretty much it. So if you look, that's a kind of a hidden.
Because I worked it, and I got to that point, and I could not get past that point to
Yeah.
get to the rest of the
Right.
problem. So
Yeah.
I lost the attempt, but I got partial credit.
Yeah.
And
So now you can go back and
work on
kick it again.
from there.
And that's pretty much it. I mean, it's kind of I threw it in there on purpose to not to cause people headache or massive headaches, but to, you know, to like, and believe it or not, that is the question that I get all the time. Where's the other angle? Where's the other angle? You know?
Yeah.
And then when you look back at it, you're like, oh, now I see. So I'm doing it for a reason. I'm doing it so that people will realize, you know, actually that this is the case. So.
And isn't that law of cosine?
Well, this is
Not law of cosine, but
this is kind of if you think about where it came from, it's kind of interesting. I can't go down. Oh, wait a minute. Okay, wait. How do you do this? I think if you zoom, there we go. It comes out of this concept. If you had say you had a rope that got to here, and say it was like this. So it was somewhere out of here, and you know, somebody's pulling here and pulling there. So the first thing you do is find that vector, say R, and then you find the unit vector. And so you'll have a unit vector, say, you know, equals to, or say you just had, I'm going to make up R. Say it's, if this is X, well, let's make this X and this Y and this Z. Let's say that distance looks like 10, and if that's 10, maybe this is 12. And if that's 12, maybe this is 9. So your R looks like 10, plus 12J plus 9K. Now, if you think about it, let me do MATLAB because I'm too tired to do it any other way. But here, I'll do it this way. Okay, so if you look at the length of the rope, it's equal to square root of 10 squared plus 12 squared plus 9 squared. That's the length of that rope that goes out to that point. And so now, I don't know what that would be, but here, let's put in R. R is equal to, and I'm going to write it as a vector. 10, 12, and 9. Turns out, in MATLAB, he loves, well, you know, it's easier to present it this way. And put it a comma. I'm going to make it a row one so I can see everything at the same time. So see everything at the same time. So now if you do a norm and just R, that turns out to be the length of the row. You know, so you do. And if you plugged all that in, it'd spit that answer out. Right. So if you did that, it'd be 18 point, the length is equal to 18.02 and some change. And now you want to find a unit vector that points in that direction. So you end up with the unit vector. Well, that's just the R, oops, here, over its own length. So this is the 18.02. So what's cool about that, you can type in U is equal to R divided by the norm of R. So you get these funny numbers. So that's 0.5547I. Oops, that's not what I wanted to, here, I wanted to hit the other key. 0.6656 J, that's a unit vector pointing in the 44992. It turns out, though, that unit vector can be represented by this: cosine alpha I plus cosine beta j plus cosine gamma k. And then if you look at it, well, that's actually, see if I can do a decent job. That's alpha, it's out of the plane. This is beta, and this is gamma. And there's a relationship between those two. I mean, those three, I'm sorry. So if you look at them, you take this unit vector, and then you say, well, what's the norm of the unit vector? Turns out to be 1. So then you're like, hey, wait a minute. So that means U, which is equal to the norm, is equal to 1, which is equal to cosine squared alpha plus cosine squared beta plus cosine squared gamma. And that's where that relationship comes from. And now, believe it or not, if you want to find them all in one big swoop, A cosine degree of U, and that tells you the angles right there, 56.31. So alpha is equal to 56.31 degrees. And gamma, and I don't remember, but I can do that, 48.27. And then 60 point something, anyway, 05 and some change. But what's funny is if I alter either one, any of those, changes them all. So, and that's where that comes from. So if that makes sense to you.
Gave me a little perspective on it,
Yeah.
rather than it just being given to me like I can understand more.
Yeah. You know, you can go pluck out the equation, that's fine, but then kind of having a feel for where it came from is a good thing too. Actually, it's a very good thing, so. So any of the others yet, or you just still?
Still working on them.
Okay.
That was problem 3 on the midterm, and then I've got all of them except for problem 7. I jacked up on one of my numbers.
Oh, okay.
At the very beginning.
Oh, okay.
I just got to spend some more time just redoing it.
Okay.
Be all right.
Yeah, and the finals the same way. Actually, I don't remember how I shuffled them. See, I knew the problem, but I didn't know it was number 3. So I may have, in my mind, I may have had 1, 2, and 3, but it may have been 3, 2, and 1 or something. So I don't remember. But it's all good. It works. So.
Well, that may not be the same for each person. I don't
Yeah.
know that.
Yeah, the numbers won't be the same. Everybody will get a different set of numbers. And then when you go back to do your second try, it'll give you a little different set too. So, and that annoys people, but you know, if you're very organized and you lay it all out, and then you're like, okay, right, and then you go back in and you fix it, and you're like, oh, okay. So, so that's why I just do 5 tries and just go with it. So I may go into, let's see, if you don't have any other questions, I may, see, today is Monday, right? Or is it? Yeah, okay, so we'll have a Wednesday or two, so so what I was thinking about doing is doing something that's not truly on the test, but something that might lead people towards what they're gonna do in mechanics and materials. And it sort of led to that on Friday, and I was gonna do one more thing on it today, if you don't mind. I mean, it's kinda, you don't need it yet, but, I was sorta, okay, so let's do it this way. I mean, I hesitate to do it, but at the same time, you'll see it again. So if you have f of x, which is equal to, say, I'm just going to make up numbers, 100 pounds per foot, and then say your beam is, I don't know, 10 foot long, so the equivalent load would be 1,000 pounds total. And it would be distributed such that 500 pounds would be sitting on the left and 500 pounds would be sitting on the right. And so, does that make sense?
Yes.
So, eraser. So I'm going to take that off, take this off, and I'm just going to put my 500 here and my 500 here. So the reason I put this in there is that eventually, let's see if I can make this go down. I cannot unless I do that. Eventually the goal is to list what's commonly called a shear and then a moment. And so if you just slice it at some arbitrary x, and then you want to know, well, it won't go any further than that. Maybe if there we go. If I do a shear diagram, a thing where I have, that was weird. I don't know why it does that. It's still 100 pounds per running foot. I don't know how many feet I've run over here. I'm going to have a moment, and I'm going to have a shear. Oh, and I'm going to have 500 pounds. So if I look at this and make it dependent upon x, then this will be equivalent for a shear diagram. It would be equivalent to a load that was 100 times x sitting there, 500 here, that's 500. So if you wanted to know that, sum of the forces in the y direction equals 0, and I'll make that go positive. And this is my shear, minus shear, minus 100x plus 500 means my shear looks like, okay, so if I move that over, 500 minus 100x. And since x can go anywhere from 0 to 10, yeah, you can just put it in and evaluate it. But if you want to plot it, let me see if I might have to zoom it out. So you put in x equals 0, it got 500. So I say I got 500 here. I don't think this version has a ruler. My version at the house does. I don't see. They change these versions so often, and there's so many different things. It's so confusing. But it has if you look at it, it has a negative slope And if you put in a value of 10, then you get 500 minus 1,000 gives you minus 500. So it goes to minus 500. And here, I'm going to stand up and lean to the side. Oh, wait a minute. Maybe I can use this box to become a ruler. Okay, that's what it looks like. Now, the reason I even start this is because if you look at the load, okay, some people will put that in. There's different textbooks use different things. I just used the f of x equaling to 100. And so if you look at the relationship between this thing and that thing, okay, so let's see. But technically, if this is positive, then this would be, actually from a functional viewpoint, it would be a minus because it's going down. And so then if you look at this and you stare at it, it turns out, for this case and all other cases, it turns out that this is the case. However, it also turns out that v is equal to the integration of, let's see, f dx. Without, I guess I could put this,
F of x.
yeah, f of x dx. And so it turns out that's kind of a relationship that sticks regardless of what you've got.
So it would be evaluated from our length, like our minimum length of 0 to however our longest length is.
Right. Now,
in this case, it's 10.
Yeah. However, in this particular case, what you would want to do is you'd want to open it so that you could, there's definite integrals and indefinite integrals. So if you integrate, if you have something like this where you put in, say, minus 100, and then you integrate it and you're like, I don't know the limits yet. And then you get minus 100x and then plus a constant integration, which I don't know if they, I don't know how they do stuff like that, so I'll say constant 1, instant. And so then they sit there and you're sitting there staring at that. It turns out to fulfill this, that has, okay, so let me state it like this. To fulfill this easily, or the most efficient way, you could say what is the f, or not what is f of x, but what is the shear at x equals 0. Okay, so if you do that, what does that amount to? Well, that amounts to 500. Now, the way they treat this is they call this a boundary condition. D. So they'll call that a boundary condition. So now that you're using the term boundary conditions, you're starting to say, hey, wait a minute, we use that in differential equation. And in fact, that's kind of what this is. Oops. Never seen that. So then the next question is moments. Let's do the moment. Okay, I don't know what happened there. Do the moment off of this picture. So if I'm doing it off that picture, let me shrink it down and I will, well, I guess I can do it. Here, I'll do it this way. I'll draw the same picture here under it. Now, here you go. Let's see if I can. The moment does exist here, but I just didn't use it. I'm just going to redo the picture and then zoom back in on it. So if I'm just looking at this picture, oops, and I'm saying what you do there is you say pick that spot because that's the spot that's the internal load. Sum of the moment equals 0. And we'll call this positive. which gives me this one, plus, okay, this one goes this way, which that's a plus, and that's a 100x times this distance is x over 2. And then I got this 500 pound going that way. And that's a minus. Minus 500x. So now, since this is positive, I guess I really need to move that to the other side. So the moment as a function of x equals to, since that was positive, it becomes 500x minus, I'm hesitant to put the 2 in there, but I think I'll just take it as a 50x squared. But I'll go ahead and take that out. Now let's make sure. Okay, so first, I got to be able to put an x equals 0, and that'll give me a moment equals 0. As far as a boundary condition is concerned, what that means is this. Okay, let me see. Eraser. That means, okay, so here, let me do this first. I'll do the lasso thing and move him kind of right there. And then I'll make it a funny, no, I already got that color. How about green? So what I'm going to do, put a moment on the left end, which is 0. And then I'm going to put a moment on the right end, which is 0. So there isn't a moment applied. The beam is allowed to flex. It's sitting on its things. It can do just like that. So it doesn't have a moment applied over there. If it was cantilevered, say welded into the wall, then the wall's going to twist against it to keep it, and that'll be another boundary condition, which you'll deal with in mechanics of materials. But for right now, we'll say there's no moment sitting over here on the left or on the right. Now, does our equation bear that? Okay, so hang on. Let me go down here and find it. Okay, so if I put in x equal to 10 pounds, what do I get? So, yeah, 500 times 10 minus 50 times 10 times another 10. And we're happy now because that and that equal, and it becomes 0. So it satisfies both boundary conditions. Now there's something bizarre about this, and this is bizarre and always true. If I take a derivative with respect to x, then nothing happens there except that the x goes away. Minus 50, okay, x squared. Okay, so I should have, okay, so do this, that. I should have put the 2 in front, but it's okay. So I get 500 minus 100x. Lo and behold, that's what that is. And so it's not just by luck, chance, or whatever. It turns out
It's the same as what's the V again?
the shear.
The shear.
Yeah. So if you look at the equations, okay, so listing them out, I'll make a little kind of funny ongoing table that's not really that great, but if you have a load as a function, as some type of function. Now I'm going backwards, but it's okay because we can do this either way. You get that. Oh, here. But you can also, let's see if, you can go one other step and do this. Which I guess I should do that, which means, okay, the second derivative the F, and I guess I really need to put the X, is equal to the moment. Wait, no, here. Let's just leave it like that. Now we don't want to complicate things yet. So we'll leave it like that because actually going further, that's the duty of mechanics of materials. But actually what you find out is the total equation becomes this. And I think I mentioned it in the last video. The minus or plus, depending on the way your sign convention is. So it turns out that's the differential equation for beams. So then the next question is, and this is something okay, so I didn't plot that. Okay, so if I plot this thing up here, what do I get? I start with nothing, and then say, just out of curiosity, what's the moment at x equal 5? It's equal to 500 times 5 minus 550 times 5 squared. Okay, let's just find that out. 500 times 5 minus 50 times 25. 1250. Turns out, just from symmetry, it's going to be parabolic.
1250 in the center.
Yeah. 1250 in the center. Now, I'm going to monkey around for a minute, and what I'm going to do is I'm going to try this. Okay, so I'm going to do a clear SYMS. I'm going to take SYMS and call it X. Do I need anything else? I guess I don't need anything else. Okay. So, if I have, how do I do that? Because I don't have a term. So I do, gosh, that's going to be boring. F is equal to 100. Actually, I should say minus 100. Okay. So, if I go up here, and I look at that equation, I got to do, I think it's integral. I think integral is int. F is equal to integral F. So he actually, what's interesting about MATLAB is he doesn't really give you a boundary. He just plots that out. There's no constant integration. So the question is, how do you put that in there? That's a good question. So the left end was, what was it, 500? I think it was 500. Oh, no. Wait a minute. Did I put in too many zeros? Oh, sorry. That's the x value. So if you x value from, how do you put constant except the integration in here? I guess you would just have to know that. So if you did a plot, I guess I need to put in the value, which it is shear equals to, and then you just did a plot of shear. Let's see, let's just try that first. There's another thing called, I think is it called easy plot? Okay, now so it doesn't do you any good because it's gone too far, but I can do easy plot maybe from 0 to 10. Okay, so it looks like that. The problem is that's not the value, so you've got to say the shear plus 500, and there's your actual shear plot right there. Then your problem is, you need to, moment is equal to the integration of the shear evaluated with respect to x. I think it will automatically do that. So then you have your moment, but if you do EZ plot of your moment from 0 to 10, well there I think you just lucked out. And the reason you lucked out is because the constant integration there is 0. So there's your moment diagram. So, and I think you can do a subplot to put them together like I did over here. So you can have the shear on top of the moment. But let's try something bizarre now. Okay. Okay, so I'm going to take a point load. F is equal to, is it delta? Let's say it's 1,000 pounds times delta of x minus 5. Oh, let's see. Let's see if I can find MATLAB delta function. I mean, oh, it's different than, it's Derek. Okay, that's what it is. Okay. Let's try that. Did I spell that right? I don't think I did. D-I-R-A-C. Okay, now, but do something interesting here. Go back to the shear. And then do a plot. What you see is a step function. So like, let's see if I can go back. So I was successful in doing that. So what I'll do is add and make a new problem. Okay, so my new problem is a beam 10 foot long in which 1,000 pounds sits right in the middle. Now the F is equal to what? And it turns out it's actually equal to 1,000 times the delta function at x minus 5. So that still means there's 500 pounds on the left, 500 pounds on the right. So the shear diagram will be 500 and then this. Why? And that's pretty easy because if you're to the left of the load, so in region 1, which is here, and region 2, which is between this load and the end, you have 500 pounds, and the shear is going to be nothing more than 500 pounds. So how do you do that on MATLAB? You do it the same way. Now, the problem is, I think, yeah, I had the 1,000, had this, and I think I did okay, 500 pounds, and then you look at the plot, looks like that. Although, wait a minute. Yeah, I think I have to look at that for a minute. I think you're right, because this has to be, like I said last time, minus, then the integral, then the plot. There you go. Oh, I think I goofed it up there too. Let's see. Don't tell me that this thing, there's no way. Yeah, but it may be. Wait a minute. So For some reason, it doesn't show the vertical line there, but that's okay. Then the question becomes, what is the moment? Okay, let's see. Okay, I can go back up until I can find the moment. Okay, there you go. Now let's do a plot of the moment. Now, that's definitely goofed, because there is no moment applied to the left end. So you got to make sure you're matching your boundary conditions, and that is not one of them. So if you look at the...
Isn't the boundary condition 500?
Well, but okay, so the boundary condition is 500, but, okay, so this is your shear, and your moment diagram should look... It should look like a straight line, goes to there, and it goes back down to here. So it should have a 0 here, because there's no moment applied here. And for that matter, there's no moment applied here. So I got to make sure, I mean, I can get the general diagram, but the constants of integration here has to be such that the boundary condition here, here, and for that matter, all of these end conditions have to match what's applied on the end. And so actually, if you look at this from a moment diagram, here's what you see. You're here, 500. The moment is going to be, and this is x, by the way, 500x. So really, if you're looking at this, where's my map? There it is. So that's kind of interesting here. So I've got to really put a, if you're doing this in MATLAB, you got to be careful that you, okay, so if I put in SUBS, this sounds weird, but, okay, so let's see. Moment for the diagram, this may sound weird. Let's see, to the moment minus SUBS, substitute the moment for x equals 0. And now if you plot that, that'll give you what its value actually is. So that's the actual moment diagram. This is a weird thing, absolute value of x minus 5. If you think about it, this is a value that sits right here, and it's symmetric about the x equal 5. But MATLAB handled it. Now here's what's bizarre, and it's really not that bizarre, but you can add both of those solutions together. But we're at the end of the class anyway. But so this is not required for this class anyway, but you will see this in mechanics of materials. And that's the only reason I'm doing that is sometimes I do the moment and shear diagrams, but actually if you look in the text, it's the asterisk section saying that it can be delayed until mechanics of materials. So I figured I'd just throw it in there so at least when you get to mechanics of materials, it's not something like brand new that you've never seen before. Huh?
We've seen it once.
Yeah. It'll be probably presented differently, but that's okay. And MATLAB can actually take a derivative of a spike function, which is what that is. Yeah. So I guess I'll stop the stream. Let me see. Okay, wait.